Hello everyone. Today we'll be solving Berland Federalization. Right. So today we'll be solving the problem Berland Federalization. Right. So this was asked in the testing ground. Done. Codeforces testing ground. Done. So what the question states here? You can just go through the question. I'll just summarize the question so that it will be easier for us to solve the problem. Right. So let's see what the question states here. So we are given a tree, and just give me a second. 1 second here. Yeah, we are given a tree with n towns, right? So we are given a tree with n towns and n minus 1 roads. So this is nothing but the towns and this is nothing but roads, right? So just remember this. We are given a tree with n towns and n minus 1 roads. We need to split it into connected states so that one state has exactly k towns, right? So we have to split it into the connected states so that one state has this one. Just give me a second. One state has exactly k towns, right? This one state has exactly k towns. This is fine. We may remove some roads, right? We may remove some roads so each state in a connected component minimizes the number of removed roads, right? So we may remove some roads so each state in a connected component minimize the number of removed roads. So what we need to output then, or what we need to calculate, or what is our main goal here? So we need to output the number of removed roads, basically number of deleted or removed roads here. This is fine. We need to output the number of removed roads. This is the question basically. Mainly what we need to do here, we need to output the minimum number of removed roads and any list of their input indices and any list of their input indices, right? So this is the main question. So I hope the question part is completely clear. Let me read this one again. So we have been given a tree with n towns and n minus 1 roads. We have to split it into the connected state so that one state has exactly k towns, right? So one state has exactly k towns, right? So we may remove some roads so each state is a connected component that minimize the number of removed roads, right? So what we need to output here or calculate, we need to output the minimum number of removed roads and any list of their input indices. Again, what we need to do, we need to output the minimum number of removed roads and any list of their output indices. So I hope this part is clear, man. Completely clear, right? So this is fine. Now let's come to the approach part, right? So just give me a second. I hope the question part is completely clear. All we need to do is we have to output the minimum number of removed nodes, removed roads, sorry. So removed roads and any list of their input indices, right? So whenever I hear the this one graph and trees, it will automatically go to the nodes rather than roads, this one, right? So here it is roads, not the nodes. So this is fine. That is the reason I'm stuttering. This is fine. Now, let's do one thing. Now we have been given n here, so this is nothing but the k. So these are nothing but the edges. 1, 2, 2, 3, 3, 4, 4, 5. Right? So 5 is, this is nothing but the n. This is nothing but the k. This is nothing but, these are nothing but the edges, connected edges. Right? So accordingly with the question that I have read. So 1, 2, 2, 3, 3, 4, and 4, 5. The output that we need to get here is 1, 2. Right? So this is fine. Now, same goes with the input 2 as well as the input 3, or the example 2, example 3. This is fine. Now, as we are completely clear with the question and the input output part, let's do one thing. Let's quickly discuss the approach followed by the complexities and then let's write the code. As usual, let's discuss the approach first. Yeah, let's consider the same first example that they have asked in the question. We have n5 and we have k here 2, right? So this one edges we have 1, 2, 2, 3, this one 3, 4, as well as 4, 5. This is fine. These are nothing but edges. So the output that we need to get here is 1, 2, right? So let's move on with the step-by-step explanation. One more thing. So we will be making use of dynamic programming here, right? DP on trees. Basically this is tree based question and we will be going with dynamic programming on trees, right? So along with the this one DFS and reconstruction pattern, right? So reconstruction pattern, right? So I hope this part is clear. Just remember this one for now. So we'll be making use of the DP on trees along with the DFS and reconstruction pattern. So this is fine. Now let's move on with the step by step this one explanation. So n we have 5k equals to adjust this one we have already discussed. This is fine. Let's move on with the next part. So I'll just show you the DP table, man. Right? So this is nothing but DP of U and S. Right? So this is fine, I guess. Just give me a second here. Did I miss anything? Mm, 1 second. This is fine, man. We will be going with the DP of U and S. When I say DP of US, this is nothing but the minimum cuts for a connected component of size S that is rooted at U. Just remember this one. So I have clearly mentioned this one just in the form of theory so that further you don't get confused. So this is DP table for the DP of US. DP of U and S is nothing but the minimum cuts for a connected component of size S that is rooted at U. And DP of U0 is 1. DP of U0 is 1 means cutting parent edge, right? So means cutting parent edge. This is fine. So now let's go with the node U. First, let's go with the node U. This is nothing but DP of U0. This is nothing but DP of U1, and this is nothing but DP of U2. Right? For the node 1, DP of U0 will be 1. This one 1. For the 3 also it is 1. 4 also 1. This one 5 also 1. Initialization part basically. DP of U1. So same thing, but this one for the 5 it is 0. Right? So we have 1, 2, 2, 2, 3, 3, 4, and 4, 5. Right? So DP of U1. So this one will be 1, 1, 1. Again, this one will be 0. For here in this case, it will be 1, 1, 1. DP of U2, it will be 1, 1, 1, 0 for this last but 1. And for the last one, it will be infinity. We'll be giving infinity. This is fine. This is the DP table. This is the DP table basically, right? So this is fine. Now let's read this table step by step, right? So node 5 nothing but the leaf. Node 5 is nothing but the leaf, right? So we are considering 5 alone, just 5 alone. So DP of 5 1 is 0. DP of 5 1 is 0 accordingly with the DP table that we considered. This one 5 1 is 0, right? So this is fine. Now node 4 it can merge with a child 5, right? So we will be considering 4 and 5 again. So you can just check the DP table that I have written and come back here. So I'll not go step by step. I'll not go to the DP table and I'll show this one. You can just check that one, right? So you can just go to the video, go to the previous part of the video and just check that one. So we can just merge. We are just merging with a child 5, or we can merge with child 5 here in this case, right? So we'll be going with a 4 comma 5 that gives DP of 4 2, right? So DP of 4 2, the value is 0, right? So DP of 5 1 0 because we are considering only 5 alone, right? So this is leaf, we are considering 5 alone. Next we are going with this one. This is for 5 alone. This is for 4 comma 5, and again the value is 0. So this one value 0, for this also value 0. This is fine. Now we have to consider node 3. So node 4 it comes with node 5 as well. 4 5 4 5, then we are going with the 3. So this is best for two nodes, nothing but 3 and 4. So we have you see 1 to 2, 2 to 3, 3 to 4, and 4 to 5. 5 is a standalone node, quite obviously, right? So 1 to 2, 2 to 3, 3 to 4, this one it is best suited for two nodes itself, right? So this one for the node 3 again will be considering in the group 3 4, or we can consider 3 5 as well, right? So this requires one cut. Again the value DP of 3 2 is 1. So this one 3 2, right? So this one is 3 2 and value will be 1 basically, right? So DP of 3 2 value is 1 according to with the DP table. So just give me a second here, 1 second. 3 to 1, this is fine. 1 the value that is coming from the DP table. So this is fine. Now we have the best two node groups again for the 2, right? So we can just go with the 2 3, right? Edge we are considering, right? So node 2 this is best suited for the 2 node group again, right? So this is not the individual like 5. So we will be going with the this one 2 3, but this needs cut again DP of 2 to 1. So this 1 2 2, the value is 1. You can just check it. So the final one, we are left with the node 1. So this is best, again this is best suited for the 2 node group, and we can just consider 1 2 here, and 1 2, the value dp of 1 2 will be 1. For all this this one 3, the value is 1, and for 5 and 4 5, the value is 0. This is fine. This is fine, I believe. Now let's go with the decision step, man. Let's see. When I say decision step, we have to try all the nodes. Nothing but root 1, root 2, root 3, root 4, root 5. We'll be trying all the roots here. Right. So we will be going with the root 1, root equals 2, root equals 3, and root equals 4. 5 is standalone. So we will this one. This one, what do we call, we'll ignore for now. So we will be trying only all the roots, right? So first dp of 1 2, we have got the value 1. Dp of 2 2 is nothing but 2, because dp of 2 2 plus 1 we are going with indexing. So this is basically the indexing starts from 0, so we need 1 and 1 based indexing here. So this one will be going with plus 1, right? So except for the first root, we are ignoring that, right? So we'll be going with will not be adding 1. So this one, dp of 1 2, for dp of 1 2, so this one will be dp of 3 2, this one will be dp of 4 2 plus 1. So this one will be 1 plus 1. So this one again 0 plus 1, this one will be 1 plus 1, this is 1, the value 1. This is fine. Now both 1 comma 2 and 4 comma 5 requires one cut, right? So code keeps the first minimum, so we will be considering 1 comma 2, right? So both of them requires one cut. So first code, what it does, it keeps the first minimum that we get here is 1 comma 2 rather than 4 comma 5. So we'll be keeping 1 comma 2 here, right? So this is also the correct one. 4 comma 5 is also correct one, but both 1 comma 2 and 4 comma 5 requires one cut. So code will keep the first minimum cut here in this case, right? So 4 comma 5 is also correct. Just remember this one, right? So this is fine. Now let's go with the reconstruction part, right? Let's go with the reconstruction part. This is also one of the important this thing uh, part basically within the code. So at node 1, what we will do, we will take one node from the child 2. We'll be taking one node from the child 2. At node 2, we take 0 nodes from the child 3, right? So the cut edges I have shown here, this is nothing but the 2 3, and the edge index is nothing but 2 here. Edge index 2. This is fine, man. The final answer that we got here is, so t equals 1, right? At node 1, we take one node from child 2. At node 1, we take one node from child 2. At node 2, we take two this one 0 nodes from the child 3. Cut edges is from 2 to 3, so edge index is 2. So we have to go with the index, right? So this one here, cut edge we will be considering, so this one will be 2, and we are considering t equals 1 because at node 1 we take one node from the child 2, right? So the t is 1 and the cut edge is 2. So the final answer that we get here is 1 2. We'll be displaying this one 1 2 as the output, right? Output. So this is the output that we got here, 1 and 2, which is equivalent to the output that they have given for the this one, example 1 within the question. Simple, right? So this is how we will be making use of the dynamic programming. uh, I have shown you the reconstruction step as well. So for this one, we'll be making use of the DFS, right? So we'll be going with a depth first search, right? So let's see the same thing further, how we try to implement in the form of code, how we try to articulate in the form of code. Let's see that one in the future. Now as we are completely familiar with the approach, let's do one thing. Let's quickly discuss the complexities part, man. When I say complexities part, what will be the time complexity and the space complexity here? The time complexity would be big of n into k square. So why it will be big of n into k square here? Just give me a second here, 1 second. Yeah, so for every node that we considered, we have to, or we were merging children with a knapsack like loop, right? So for every node, we merge children with a knapsack like loop. That in worst case, it costs big of k square, and summing over all the nodes will give us big of n into k to the power of 2, right? So big of n into k to the power of 2, this one. And what would be the space complexity here? The space complexity would lead to big of n into k plus n square, right? So this one, big of n into k plus n square. So dp and choice use this one big of n into k, while RID is big of n square. So array is nothing but the some this one variable that we'll be making use of. So don't get confused here. So this is safe for this one, n less than or equal to 400, right? So accordingly with the constraint, we'll be going with the adjacency matrix as well as the adjacency list as well as the other arrays that add up to this one, big of n, right? So overall space complexity would lead to big of n into k plus n square, right? So the time complexity and the space complexity for the code that we'll be writing in the future would be big of n into k square plus big of n into k plus n square, right? So now as we are completely familiar with the approach and the complexities, we are good to write the code. Let's start writing the code. Let's start writing the code now. So I'll just come here. So first we'll be making use of the this one fast input and output. So I'll just go with, or I'll just import here input output package. This is fine. Now let me import. We'll be making use of different utilities as well. So I'll just this one import the utility package here. So let me go with public. So here class, uh, this one let me give here main. So you can just give any name here. This is fine. Now what I wanted to say here, I just give any relevant name accordingly with the question, right? So according to the question. Now let's make use of the large value that is used as infinity for the DP, right? So they have strictly mentioned this one in the question itself. So I'll just give here static final end, so infinity. So this one will be 1. This is nothing but 10 to the power of 9, I believe. This is fine. Yep. This is fine, man. So this is just the large value that is used as infinity for the DP. Next, let's do one thing. Let's go with the number of edges and the target size k, man. So here on this case, this will be static int n comma k. So this is nothing but the number of nodes and target size k. Now let's go with the adjacency as the static arrays, nothing but the edge lists that is stored in the arrays. So we have to consider head to nx as well as the id. Right, so let's do that. So I'll just go with static here. So this one is fine. Int head to this one nx. So this one will be id. Now let me go with the static here. Int ec equals 0. This is fine. Now this one ec is nothing but the edge counter, man. Edge counter, because each undirected edge will be stored twice in the arrays. So that is the reason we have initialized ec to 0. Don't get confused here, right? So now let's go with a deg, nothing but the this one degree, right? So degree to size children arrays, right? So let's consider, we have to consider parent as well along with it, right? So I'll just go with static here. Int comma parent, right? So this is fine. We are done with this part, man. Now let's do one thing. Deep Let's go with a dp of us. If you remember the approach, I said dp of us and I showed you first, right? So that is nothing but the minimum boundary or the cut edges in the subtree for the connected component of the size, right? That is less than or equal to, if I remember correctly, just give me a second here. So basically it is the minimum boundary or the cut edges, right, in the subtree for the connected component of the size that is less than or equal to that contains u, I believe. So let's see the same. Let's do one thing. Let's go with the dp table, man. uh, this one I have to write or I shouldn't write, I don't know, man. We haven't initialized dp yet, right? So let's do one thing. Let me go with the static here in dp. This is fine. Now let's do one thing. Per node children, we have to go with the per node children listing, right? For the reconstruction purpose. So I'll just go with static here. This one int, this is ch, this is fine. Now let's go with the choices uis, meaning how many nodes taken from ith child of u, where we form size that is less than or equal this one size s at u, right? So let's see. This will be static. So this one will be int. Uh, this one will be choice. So this is fine, man. Now let's go with the edge indices lookup. So this one will be static. uh, int. So this one will be, let me go with RID. So if you remember the space complexity, so I said RID, the keyword RID will be making use of, right? So this is nothing but the RID. So this is nothing but the edge indices lookup, right? RID of UV will be going with nothing but input index of the edge U comma V, right? This is fine, man. Now let's do one thing. Let's write the first helper method, add edge. We have to go with the add edge. Add edge helper method, what it does, let me tell you now itself. So it adds the undirected edge, nothing but U to V with the input index IDX into the adjacency arrays. Let's see the same thing in the action. Let's try to implement the same thing in the form of code. So this will be static. So this will be void uh, add edges. So this one will be int u, int v. So this one will be int index. Index, I'll just go with a idx here. This is fine. Now this one will be to ec. This is fine. Let me assign this one to the v. Right. So this one id of ec. So let me assign this one to the idx. This is also fine. Now nx of this one EC. So this one, let me assign this one to the head of U, right? This is also fine. Finally, head of U. So this one, let me assign this one to the EC. So we have to increment this one, right? So this is fine. Same thing, let me copy this one and make the necessary changes in the next line, man. Right? So I'll just go with same thing here. So this remains same. Instead of V, let's make this one U. Right? So this is fine. ID of EC remains same, IDX remains same, and X of EC equals head of this one. Instead of here head of U, this will be head of V. So again, here instead of head of V, head of U, this will be head of V. So this remains same one. Yep. We know what we are doing, right? So we are just adding the undirected edge U and V with the input index IDX into the adjacency arrays, right? So now let's try to increase the degree counts, man. So this one will be DEG of U. So let me increment this one. Also DEG of this one V. This is fine. Let me increment this one as well. Now let's store the edge index for both the directions. This will be RID of U V. So this one will be, let me assign this one to the index. Also RID V U. This is also fine. So let me assign this one to the index as well. So now this is fine. Now let's go with the DFS. As I've said, we'll be making use of the DFS, right? So why DFS here? So we have to build the parent-children relations, right? And also we have to fill the DP of U star. Nothing but when I say DP of U star, we have to go with the knapsack merging children, right? So this one we had discussed on the approach. While discussing the approach, I had stressed this one. Basically, we'll be going with the knapsack merging children, right? So we will be going with the DFS because it builds the parent-children relations as well as it fills the DP of U star by knapsack merging children, right? So let's go with the DFS helper method. So I'll just go with static here. This one void. So this one will be DFS. So let me go with the parameters in U and P basically. This is fine. Now, within the DFS helper method, let's record the parent first. So this one will be parent of U. Let me assign this one to the P, and let's build the children list, right? So let's build the children list now. Nothing but number of children is equivalent to the degree minus 1, right? If it is having a parent, I'm speaking of, right? So here we'll be building the children list. Nothing but if the number of children is equivalent to the will be equivalent to the degree minus 1 if it has a parent. So here in this case, this will be int m equals degree of u, dg of u minus, so this one will be p equivalent to 0. So this is fine. 0, this is 1. Now this is fine, man. Yep, I have just made use of the ternary operator. Yeah, it's good that I made use of the ternary operator, or else I would have written this one. condition. This is fine, man. Let's go with the temporary array for the children as well. So here this one int. So I'll just give kids here instead of the child or the children. So new. So this one will be int of. So we have to pass m, right? So this is fine. So we are just going with the temporary array for the children. Now let me assign t equals 0 here. This is also fine. So let's go with the for loop, man. Now when I say for loop, we have to iterate the adjacency list of u, right? Accordingly with what we have discussed earlier, we have to iterate the adjacency list of u. Now for that, let me go with for here int e equals head of u. This is fine. So this one will be e not equal to 1. This is also fine. E equals nx. So this one, let me pass e here as well. Within this for loop, what we'll be doing, let me assign v to e. So this one will be int v equals to e. This is fine. Now let's skip the parent link, man. When I say let's skip the parent link, if v is equivalent to the value p, then let's skip. So not clonable, man. I wanted to make use of the continue keyword. So why this is taking like this? Continue. This is fine. Now, so let's go with the recursive part. Nothing but we will be going with the DFS into the child first. So we'll be making use of the post order traversal. So we have solved n number of this thing problems on the post order. So I'm not going to explain what is post order and all. So you have to know post order. By this time we have solved many problems already. We have solved the problems on trees, lead code problems as well. At this time you have to know, right? So if you don't know, please do go through the notes that I have provided, right? So this is fine, or you can just go through the LinkedIn post that I have posted, right? So now let's go with the DFS into the child first. So we'll just go with DFS here. DFS of, let me pass v comma u. This is fine, man. Now let's record this child, meaning kids of this one t plus plus. Let me assign this one to v, meaning we have to record this child. This is fine. Let me come out of this one entirely. So now we have to save the children array for reconstruction. So this one will be ch of u. So let me assign this one to the kids. Now let's allocate the choice table for this particular node. So this one will be choice of u. Let me assign this one to new int of m, then k plus 1. We have to go with k plus 1. Yeah, this is fine, man. Now let's go with the knapsack over children. When I say knapsack over children, this is nothing but we'll be going with a f of s that is equivalent to the best cost after processing some children, right? So let me write it on this way in the form of code. So I'll just go with f. Let me assign this one to the new initialization part. So this one will be k plus 1. And also we let's fill this one initially with the infinity. So I'll just go with uh, arrays dot fill. So this one will be f comma infinity, right? So this is fine, man. Now we have initialized this one with the infinity. Now we'll be going with f of 1. Let's assign this one to the 0. This is fine. Now let's do one thing. Let's process each child and let's merge, right? So let's go with the for loop here. Int I equals 0, I less than m, so I plus plus. So this is fine. Int v equals kids of I, right? So this is fine. Now int nf equals new int of k plus 1. So I'll just go with arrays dot fill of this one nf comma inf. This is fine. We are done with this part, right? So now let's go with the current possible sizes before merging the child v. So I'll just go with the simple for loop here. If sorry, int, so we are going with s, right? So s equals 1, s has to be less than or equal to k s plus plus. So this is fine. So within the for loop, what we'll be doing here now, we are going with the current possible sizes before merging child b, right? So within this for loop, we have to skip the unreachable sizes, meaning if f of s, so this one equals infinity, then let me go with continue. So this is fine. We just have to skip the unreachable sizes here, right? So this is fine, man. Now let's go with the option one, meaning we have to cut the edge u to v entirely, meaning we don't take any node from v, right? So dp of v0 equals 1. This is nothing but the child cut, but may also be infinity if something else, right? So let's try to implement the same thing in the form of code. Let's write this one very quickly, man. So this one uh, I couldn't write it this one within the this one as well. What do you call ternary, using the ternary operator as well. This one I have to write this one completely. So this one dp of v0, if it is not equal to infinity, then let me assign the value to this one f of s. So this is fine, plus dp of v and what do we call 0. Now let me write the simple if condition here. If the value is less than nf of s here, then what we will do, we'll go with nf of s. So this one, let's assign this one to the value. Also, let me go with a choice of uis, ui and s, right? So let me assign this one to the 0. Let me come out of this one entirely. Now we are left with the option 2, meaning we have to take j nodes from child v, right? So nothing but j greater than or equal to 1 and merge into use component, right? So let me go with a simple for loop now. So this one will be for int j equals 1, j less than or equal to k minus s. So this one will be j plus plus. So if dp of v and j, so this one equals infinity, then let me give continue here. This is fine. We are just skipping impossible sizes from the child. So let me go with int value, uh, this one equals f of s. So this is fine, plus dp of v j. This is fine. Yeah. Now if value less than nf of this one s plus j. Now within the if condition, what I'll do, let me go with nf of s plus j equals val. This is also fine. Now we are left with again the choice part, right? So I'll just go with the choice of, so this one will be u, this one will be I, and this one will be s plus j. Let me assign this one to the j. This is fine. Now let me come out of this one entirely. Now let's move to the next child with the merged results. In the sense, I'll just assign this one to the f to the nf basically. Right. So let me come out of this one entirely now. So we have to write the dp of u star. If you remember the approach, dp of u star from f is nothing but dp of us for s greater than or equal to 1, right? And also dp of u0 is nothing but it is equivalent to the cut to parent sentinel, right? So let's try to write the same. First let's go with the iteration here. So let me go with for int s equals 1, s less than or equal to k, s plus plus. This is fine. So this one will be dp of u s. So this one will be f of s. This is fine. So this one will be dp of u 0. Let me assign this one to 1. Let me come out of this one entirely. Now let's do one thing. Let's go with the reconstruction part. Reconstruction, if you remember this one in the approach, we have discussed the reconstruction part, right? Reconstruction is nothing but we have to reconstruct which edges to cut, right? Basically. accordingly with the what do we call uh, accordingly with the approach that we had discussed. So we have to reconstruct which edges to cut starting at the node u, aiming to take the need nodes, right? So let's try to write the helper method reconstruct, right? So I'll just go with here static void. I'll just write recon here. This is fine. This is nothing but the reconstruct. So I'll just go with the parameters u need as well as what we need. We need cuts as well, right? So I'll just go with the array list here, which consists of type integer. Let me give cuts here. This is fine. Now within this method, first thing is we have to go with the children array. Nothing but I'll just assign kids to ch of u. This is nothing but the children array, right? So now let's process the children in the reverse order, man. Nothing but simple for loop or iteration part, reverse order, reverse iteration. This one will be kids dot length minus 1. So this one will be sorry I greater than or equal to 0. So this one will be I minus minus. So within this for loop, what we'll be doing here now, let me go with v equals kids of I. This is fine. uh Let me initialize take to this one. Let me go with choice u I. This one will be need, right? So this is also fine, man. If take equals 0, then what we will be doing, so what we'll be doing now, if the value nothing but the take, if it is equivalent to 0, then we decided to cut this child edge, right? So that's what we decided. So how can we implement that one in the form of code? Let me go with, I hope this works, man. Cuts dot, let me go with add here. Along with the add, let me go with rid here. This is fine. Let me pass u and v. This is also fine, I believe, right? Else what we need to do, let's go with a, let's recurse now. Recon reconstruct, nothing but the method name, right? Or the function name we are considering here. We took take nodes from the child v, so we have to reconstruct that one, right? So we have to go with we take and this one cuts. So I'll just go with take and cuts. This is fine now. Yep. So now next part would be, so we have to reduce the remaining needed nodes by whatever we took from this particular child, meaning need, we have to assign this one to need minus take, right? So I can just write it on this way, need equals need minus take, right? So this is fine. So we are done with this part almost, right? So not almost, we are done with this method basically, right? So this is fine, man. Now we are left with only main method, so the big main method, right? So this the code is huge actually, I'm not gonna lie. So let me go with main method here. So this is fine. Let me delete this one. What it consists of basically here, uh, so let me go with throws exception, or else we'll be getting the error. So let me include throws exception here. So within this method, so first we'll be going with the fast input output helper, in the sense we'll be going with the fast input, this one fast input, basically custom fast input. So I'll just go with fast input output, this one. Let me include now itself. I'll just copy paste that part, man. The fast input part custom, that is related to the template, that is related to the input output, basically that one of the templates that I often make use of. So I'll just copy paste that one. I'll just type the logical part. So the last part I'll just copy paste, this one fast input. Now I have included fast IO equals new fast, this one I'm speaking of, right? Fast, this has to be fast IO. This is fine. Now let we have to read n and k. So I'll just give here n equals IO dot next. This is fine. Next, let me assign this one k equals IO dot next int. This is also fine. Next int. This is also fine. We are just reading n and k, right? So now let's assign, or let's go with the initialization part. First let's initialize the adjacency head pointers to -1. So I'll just let's initialize everything that we need, man. So this one will be new int of n plus 1. So let's fill this one. Arrays dot fill of, we are initializing this one with a minus 1, right? Head and minus 1. We are filling this one with the minus 1, sorry. So this is fine now. Now let's initialize the arrays. So this one will be 2 equals new int of 2 into so this one will be n minus 1. This is also fine. Now nx equals new into 2 into n minus 1. So this is fine as well. Let me assign id to the new int of 2 into uh, n minus 1. This is fine, man. Now let's go with the degree, meaning let's go with the degree and the parent array. So this one will be degree equals new int of n plus 1. This is also fine. So parent, so this one is equivalent to the new int of n plus 1. This is also fine. So this is nothing but the degree and the parent arrays. Now let's go with the dp table that is sized n plus 1 into k plus 1, right? So I'll just assign the dp to new int of n plus 1 into k plus 1, right? N plus 1. This is n plus 1 and k plus 1 for the safer sides, basically. This is fine. Now let's go with the children list. When I say children list, this is allocated later per node. Just keep this in mind. So I'll just assign ch to new int of uh, n plus 1. This is allocated later, right? So let me give the, so let's go with choices per node as well. So this will be allocated in the DFS. We have already done this one. So this will be choice equals new int of n plus 1. We have already performed DFS. That's what I meant. So this one is fine. Sorry, man. So let me give one more array here. 3 arrays we need, right? So this is fine. One more last thing that I need to initialize here is we have to store the original input edges indices between any two nodes, meaning RID equals, so this one will be new int of n plus 1 into n plus 1. So this is fine, man. So let's move on with the further things. So let's move on with the iteration part. For int I equals 1, I less than or equal to n, so I plus plus, this is fine. So arrays dot fill, this one will be iterated value of the dp along with the infinity. We have just initialized the dp values to the infinity. Now let's go with the simple for loop. One more for loop here. We have to read n minus 1 edges as well, right? So here this will be int I equals 1, I less than or equal to n, so this one will be I plus plus. So within this for loop, so let me assign a equals input output dot next int, also b equals same thing, input output dot next int. So this is fine. Now the next part would be so we will be making use of the add edge method that we have already written. So this one add edges, right? So this one I'll just make this one as add edge rather than the add edges. So let me go with add edge here. Let's make use of this particular method. That is the reason we have written the add edge method here, right? So to make use of it within the main method, so this one will be a b I. This is fine. We have successfully added the edges with input index I. Now we have already written the DFS method here. This one helper method DFS. This is not the reconstruction, not this one, this one. So let's make use of the DFS, or let's perform the DFS within the main method now. So we have to start the DFS, or we have to run the DFS from the node 1, treating 1 as root and parent 0, right? So now I can write it on this way, 1 0. This is fine, simple, very simple, right? So now let's try the root 1. Let's try the root 1 as the starting candidate and its dp of 1 and k. So this one will be int best equals 1, comma answer equals dp of 1. Okay, this is fine. Now let's go with a simple for loop, man. In q equals to u less than or equal to n, this one will be u plus plus. So within the for loop, what I'll do, let's go with the value equals dp of u along with the k. This is fine. Now let's go with the simple if condition. If taking component that is rooted at u, that needs one, right? So that needs one basically. So this, if taking component that is rooted at u, that needs one extra cut for the parent edge, right? So now how can we articulate this one in the form of code, man? So I have to write in this way. Let's see. If val, if it is less than infinity and value plus 1 has to be less than answer basically. I hope this works. Let's see. Let me assign answer to the value plus 1 we have to go with, right? So this is fine. And we have to choose u as the root of the k side state. That meaning here we have to assign best to u. This is fine. Now let me come out of this one entirely. So let's go with the array list. Means we have to collect indices of edges to cut. So let's collect indices of edges to cut. So here this one will be array list. So this consists of integer, right? So this is of type integer. So let me go with capital I here. Now let me go with cuts equals new array list. So this is fine. Now if best not equal to 1, if chosen root is not the global root, then we have to cut the edge to its parent, right? So basically that separates this particular state. That's what we need to do. If chosen root is not the global root, then we have to cut the edge to its parent. This is what we have done in the approach as well. So this one, how can I write? If best not equal to 1, so I'll just go with cuts dot add of this one will be RID best along with a bar of best. This is fine. Yep. Now let me go with a reconstruction method. So let me pass best here k along with the cuts. This is fine. We have successfully made use of the reconstruct method along with other cuts that is inside the subtree that is rooted at best. Now let's move on with the input output part. So I'll just go with input output. So this one will be, let me type this one, println. So this one will be, if it is impossible, nothing but infinity, we have to print 0 as specified in the question, right? So let's do that one. Simple. Here if println, so this one, how can I write? So if answer greater than or equal to infinity, then we have to print 0, else we have to print answer. This is fine. Now if what if answer is greater than 0, then we have to go with a simple for loop, because we have to print the indices of the cut edges. See, in the output we got 1, t equals 1, and cut edge equals 2. We have to print the cut edge as well, right? So let's go with for int x. I was speaking of the first example that we considered in the approach, right? So you can just go to the approach part and look into it, or else you can just see in the question as well, right, directly. So I'll just go with input output dot let me go with print is enough, ln is not required. So this one will be x plus, we need to leave the space as well here. So we'll be appending the space here. This is fine. So we are just printing the indices of the cut edges, right? So now we are left with only one part, nothing but we have to flush and close the input output, right? So either you can go with a flush or you can just go with a close. Previously I had went with the flush for the previous problem. I'll just go with a close for this particular problem, right? So we are done with this part. Now we are left with only the fast input part, right? So nothing but the fast IO, right? This one. custom fast input. I said we'll be making use of the custom fast input, right? So I'll be copy pasting that one. So we are done with the logic and solving the question. We are just left with the custom out, this one, input output basically. That one I'll be copy pasting, man. This is not related to the logic, right? So this is just related to the input output part. So I'll just copy paste that one. So let me come here. So let me paste this one, right? So this is fine. So this is it for the this one. This is one of the templates that I make use of. So you can just go this one. You can just make use of this one itself, or you can just go with your own template for the input output part, man. Right? So I hope this is fine, man. Now we are done with the coding part. So before checking the code with different input output, sorry, what happened here? Before checking the code with different inputs, so let me copy paste the signature starter template here. So I'll just come here. So let me paste this one, man. So I'll just come here. Let's check with this input. We have to get the output 1 2, right? So I hope we don't get much errors, man. Oh, we have TP, so that has to be only T. So where is this? Line number 51, man. Where is this 51? Yeah. So here this has to be. Where is this T, right? Where we have initialized, we initialized only T. So this has to be T. P, I don't know why I have given P. So now error array required but int found. Line number 51 again. Uh, array array itself we have given, right? V. So this comes within the DFS method basically. So we have initialized this one with the array itself, or just give me a second here, 1 second. So this one is fine. No, we have initialized this one. Just give me a second, 1 second here. So yeah, this mistake here is this is not T basically, right? So this we have initialized this one T. This is 2. Damn, bro. This is fine, man. Now let me run this. This error has to be gone. Yeah, we're left with some two errors here. Error cannot find the symbol. 112. Let's come to 112, man. Just come here. 112 fast input out. So this one. Just give me a second here. Yeah, we are making use of the fast input output, right? So this one, it's just give me a second here. That is the reason this is giving error. Yeah, this is fine. Mm, cannot find the symbol again. Uh, the heck, man. Line number 113 IO dot next main. Oh, so this one has to be next int, not the next. I forgot to give int here. It's fine. Well, if with one error, so this one has to be array list, not arrays list. So this one again, 141. The last error. Uh, I have given array. Oh, here, this part I have given arrays list. So let me run this one now. Now all the errors are gone. Command failed. So just give me a second here. 1 second. So what are the mistakes I have done here is here in the line number 50. So this has to be I not equivalent to the -1, right? So this is fine. Now let's come to the line number 85 here. So this is fine. Now this one choice this one, see here, this we have to consider U, right? So I have typed I twice. So this is one of the things that is wrong. And one more thing in the line number 25. So tree is having n minus 1 edges here. So I have considered only n. So this will give us the wrong answer, right? So now let me run this one. Yeah, now we are getting the correct output 1 2, right? So this is fine. So let me copy this one. We have to get the output 2 3 4. Let's check the same thing here. So we are getting the correct output 2 3 4. Now let me go with the input 1 1. We have to get the output 0. Let's check the same thing here. So we are getting the output 0, right? So we are getting the correct output or the desired output for the example inputs that they have given in the question. So let me copy this one entirely. Let me hit the submit button. So here, let me paste this one and let me hit the submit button. I hope this works for all the test cases, man. Let's see. Let's wait for some time. Let's wait for some time. So now this is fine. Running on test 33. So yeah, here in the toast it is showing accepted and the verdict that we got here is accepted as well, right? So whatever the code that we have written works absolutely correct for all the test cases. So we have made use of the DP on trees along with the DFS as well as reconstruction, right? Reconstruction pattern. So this is fine. Now, yep, for now, this is it. So I hope the solution part is completely clear along with the approach and the complexities. For now, this is it. Thanks for watching, guys.